Okay, get this. What if I told you that you could get to the moon using just a single sheet of paper? I know it sounds completely nuts, right? Like some kind of magic trick, but it's actually math. So let's unfold this idea and see how a simple piece of paper can pretty much become a rocket ship. We're going to start with a really simple challenge, something you've probably even tried before. But then we're going to ask a question that kind of pushes past the normal physical limits of our world. So seriously, how many times can you do it? If you've ever tried this, you know you get stuck fast. The common wisdom, and really the physical limit for most paper, is about 7 folds. After that, it's just a solid little brick. It won't budge. But let's play a game. Let's imagine we could just ignore those pesky laws of physics. What if we had this magical piece of paper that we could fold as many times as we wanted? What do you think would happen if we folded it, let's say, 46 times? How thick do you think it'd be? A few feet? Maybe as tall as a house? You'd reach the moon. Yeah, let that sink in for a second. Not just tall, not just reaching the clouds. After only 46 folds, the thickness of that one sheet of paper would stretch all the way to the moon. It sounds absolutely impossible, I know, but the math behind it is shockingly simple. So, how on earth does this work? It's not a trick, I promise. It's a fundamental principle called the power of doubling. You might also hear it called multiplicative growth. Let's break down the actual math behind this magic. Okay, so a standard piece of paper is about 0.001 centimeters thick, super thin. With the first fold, it doubles to 0.002, then 0.004. You can see how unimpressive this looks at first. I mean, even after 10 folds, we're only at about 1 centimeter thick. You'd barely notice it. But don't be fooled by the slow start, because the explosion is coming. And then, boom! Suddenly the growth just goes vertical. At 17 folds, the paper is over 4 feet tall. By 26 folds, it's rocketing past the height of the Burj Khalifa, the tallest building in the world. And just 4 little folds later, at 30, you're at the cruising altitude of a commercial airplane. The growth isn't just adding a little bit each time, it's multiplying on itself, again and again. This is the engine behind our trip to the moon. Exponential growth. It's not about adding, it's all about multiplying. With every single fold, you double the entire stack that came before it. That's the key. So the math for each step is incredibly simple. The first fold is just the original thickness times 2. Easy enough. The second fold just multiplies that result by 2 again. And you just keep going like that. But, writing times 2 46 times would be a total nightmare. Luckily, we have a powerful shorthand for this. Exponents. That little number up top, that's the secret code for exponential growth. And for our journey, that code is 2 to the power of 46. But here's the cool part. This isn't just some fun thought experiment with paper. Once you learn to spot this pattern, you start seeing it absolutely everywhere. All right, here's a classic riddle for you. Imagine a pond with lotuses that double in number every single day. If the pond is completely full on day 30, on which day was it half full? Now, our brains want to scream day 15, right? But the answer is day 29. Because it doubles every day, it had to be half full the day right before it became full. It's totally counterintuitive, just like our paper. Or think about passwords. A simple 2-digit lock has 100 combinations. Okay, but add just 1 more digit and it jumps to 1,000. Add 2 more and you're at 100,000 combinations. Each digit you add doesn't just add a few more possibilities, it multiplies the total by 10. That's exponential security in action. So what this really gives us is a new mental tool. It's a way to wrap our minds around numbers that are so massive they would otherwise just be meaningless. We're talking from the scale of our planet to the entire cosmos. Let's start with something familiar. The human population. It's around 8.2 billion. In scientific notation, that's 8.2 times 10 to the power of 9. That little 9 tells us the scale. We're in the billions. Now hold on. Let's look at the estimated ant population on Earth. That's 2 times 10 to the power of 16. We just jumped from billions to quadrillions.
That leap is so staggering it means there are about 2.5 million ants for every single human on the planet. Just let that one sit for a minute.
And it gets even bigger. The estimated number of stars in the observable universe? 2 times 10 to the power of 23. Using exponents is pretty much the only way our brains can even begin to imagine a number that massive. This amazing tool also works for time. The dinosaurs went extinct about 2 times 10 to the power of 15 seconds ago. But the universe itself was formed about 4.3 times 10 to the power of 17 seconds ago. That tiny little change in the exponent, from 15 to 17, represents almost the entire history of everything that has ever existed. Okay, so let's put it all together with one final, really powerful comparison. When you boil it all down, there are 2 fundamentally different ways that things can grow. Let's go back to our moon journey one last time. What if instead of folding paper, we just built a ladder? With each step, you add a fixed height, let's say 20 centimeters. This is what we call linear or additive growth. To get to the moon this way would require over 1.9 billion steps, an almost unimaginable number of one after the other additions.
And here it is. You can see the 2 paths side by side. On one side, you've got the ladder. Nearly 2 billion plodding, additive steps, one at a time. On the other side, the paper. Just 46 magical multiplicative folds. Both get you to the moon, but one of them unlocks a power that feels, well, it feels like a superpower. And that leads to a final thought. From the way ideas spread online like wildfire to compound interest growing in your bank account, this powerful force of doubling is literally all around us, all the time. So the question I want to leave you with is this. Where else is exponential growth hiding right in plain